Last week in the maths class, we worked out how to find a vector's angle to another vector. Why did we do that? Because the cosine of that angle seemed really helpful. It's helpful to solve diffuse lighting on a 3D object, helped us solve refractions and reflections. This week we're going to do something a little bit more with trig and then a lot more work with vectors. And that work is going to help us crack spec highlights, rendering multiple polygons. Hi, I'm Mike Seymour. Welcome to class 3. So we looked at vectors last week, and vectors are actually rather a new thing on the scene. In fact, they haven't been around since more than a couple hundred years, really, about the 18th, 19th century. So we're going to sort of finish out vectors this week, but first a tad more trigonometry. So we've done cos. The other big one is sine. Now, sine and cos waves are just a starting point for so much stuff. For example, stuff we'll do in particles. And it's our ability to manipulate sine and cos waves that we're going to find really, really helpful as we move further. In fact, we're going to do a bit of sine wave manipulation in this class. So how does sine work? How does it work in relationship to cos? Well, in fact, they're very, very closely related. We know that cos is the adjacent over the hypotenuse. So what's sine? It's basically the other biggie. It's the opposite side over the hypotenuse. So these two curves, when we plot them on any kind of graph, gives us a remarkably similar looking, well, we call it sine wave. And that's because the sine wave and the cos wave are actually incredibly closely related. In fact, the cos wave, or the cosine of any angle, is actually equal to the sine of the same angle plus 90 degrees. So this really makes sense when you look at them side by side, rising and falling. On, say, a circle, if we map a triangle inside a circle, as of course the adjacent gets shorter as the hypotenuse goes up vertically, so too does the opposite in fact get longer. They're kind of a yin and yang of each other. Well, if we remember that sine and cos are just universal translators that get us between triangles' edges and their angles in their corners, we can go back to vectors. So a bunch of maths was worked out by a bunch of these gurus, as I said, in the case of vectors, around 1800 or so. And I'm very fond of one guy in particular, Sir William Hamilton, or Bill as his friends may have called him. We're going to call him Bill. Good old Bill died in about 1856, but not until after he'd published his lectures on quaternions, which is probably, not surprisingly, not a blockbuster of really cool math stuff. In fact, it wasn't a bestseller at all. It wasn't, in fact, appreciated until after an American physicist named Johann Gibbs published a much better titled Vector Analysis around 1884. And much like the American version of the TV show The Office, which really legitimised the UK original and of course has run longer than the original UK version, the American publication is what made Bill's work really popular. Okay, so I'll get back to that in a second, but it was old Bill walking out one day with his dog one afternoon in 1843. And Bill was trying to work out what a vector product of two vectors would be, what a cross product would mean. Now we saw that scalar products last week, or dot products as we called them, two vectors multiplied together that gave us a number or a scalar product. That's why they're called scalar sometimes. So that idea that the two dot products end up with one scalar number is one good concept, but this is the vector product, the cross product. And that gives us a vector back, not a number back. Bill wondered, what would a vector product mean and how would it work? And I guess this all hangs on one thing. If you remember last week, I singularly avoided the problem of how I would get a surface normal. We did lots of stuff with surface normals, but I never actually said how I'd get the actual surface normal. Well, later in this class, Bill and his dog will give us a vector that is 90 degrees to any other two vectors. So if we have two vectors, he'll give us a vector that's 90 degrees to both of them. In fact, he'll give us surface normals. So just to review, what we've actually worked out from last week was in fact Lambert's law. So this was named after the guy called Johann Heinrich Lambert. And we tend to think of CG as all being kind of cool new stuff done since the 80s, but in fact Johann was doing this in the late 1700s. So, Lambert's law, it states that the intensity of illumination on a diffuse surface is proportional to the cosine of the angle between the surface normal and the light, as we discussed last week. In CG, Lambert's reflection is a really useful model for diffuse reflection. So, just as an aside, an important aspect of Lambert's cosine law is that a surface, when viewed from any angle, has the same kind of apparent radiance. That means, for example, that to my eye, looking at this ball, it has the same kind of brightness whether I'm looking at the edge or dead center in the middle. This is because the ambient amount of like energy or power, if you like, that's coming off this is actually affected by the viewing angle. If I look at this baseball straight on, and this baseball is obviously made up of patches as a baseball is, that front patch looks about the same in terms of brightness as the left and the right. And the reason for that is that even though I'm seeing, you know, most of this left or right patch from your point of view as it goes to the side, in fact, because it's becoming a more oblique angle, it reduces. Otherwise, of course, that same patch, when on its side, would appear brighter and a ball would miraculously look brighter as it got to the edges. So it's an incredibly useful, sensible, everyday thing that basically dates back to optics. So the size of this decreasing corresponding to the amount of the angle or the cosine makes perfect sense. It's exactly what we'd expect to happen, and it's what we use every day. Of course, we don't think about it in terms of our eyes. Okay, so being able to work out the ambient diffuse lighting on this is really important. And interestingly, if something basically exhibits full Lambert illumination or reflectance, like we're talking about, obviously this ball doesn't, has a bit of reflectance, it's also isotropic. Now, what's isotropic mean? Isotropic simply means that it's uniform in all directions. An anisotropic surface would be something like a CD. CD, obviously, as you hold it in your hand, you get those rainbow effects. It's different depending on the angle you look at it at. And it's one of the much more complicated models of 3D lighting. Obviously, at the other end of the spectrum is our diffuse reflection. But let's see how we can head towards those really complicated shading models, such as anisotropic. So let's start also thinking about some of the other stuff that we've got to add on top and whether or not the maths that we've been talking about is going to help us with that. This is a mirror ball, and I'm going to do is move towards objects that, like this mirror ball, have very strong spec highlights. I'll come back to this in a second, but at one end of a spectrum is the completely diffuse or matte kind of ball, and at the other end of the spectrum is the mirror ball. Now, to get us heading towards the bright mirror ball is Gouraud shading. Gouraud shading was named after a guy called Henry Gouraud, and it's a method of basically being able to simulate the way that light changes, and colour, across the surface of an object. Now, in practice, Gouraud shading is like a fast cheat. It lets us achieve really smooth kind of lighting on a very low polygon count object without any kind of computational heavy lifting. And it does it by not having to compute the lighting at every single point on the object. So the way I might want to do this is I might want to model this ball in 3D, and I might model it with a set of points, not particularly many. And between those points I'm going to draw lines and produce basically a bunch of little triangles. And what I'm going to do is not calculate the value at every single point, at every single pixel across this, but rather those key vertex corners, as it were, and then I'm going to interpolate between them. I'm going to basically use more for an interpolation between two different values. I'm going to guess what the surface normal is at any value, depending on how close it is to one of those corners or vertexes. So I make an object with a bunch of 3D points. I connect the points and I get a set of flat triangles. Now this is important. These are not curved triangles. These are just simple flat triangles. And of course, every triangle will be a different color depending on how much it's angled towards the light. To stop it looking like this faceted object, we, as I said, interpolate the normals. We kind of guess what it is in between any actual readings that we've done. So, how the heck do I get these normals in the first place? I keep on talking about surface normals and saying how important they are, but I never really have given you how you get a surface normal. Well, if we have two vectors, as we saw last week, that can be converted or moved around in 3 space so that they are connected. In other words, because a vector doesn't actually sit at a point in space, but is a direction and a magnitude, I can move two vectors so their ends touch. Once their ends touch, I can effectively define those two vectors with 3 points. So the common point at the end, and then 1 point out for each of the two ends, giving me thus the direction and magnitude. And of course, if I slide that on down to 0, 0, 0, I actually really only need to give you the 2 points. But let's stay with 3 points in 3 space. If I have 3 points in 3 space for my two vectors, I have a coplanar existence. These 3 points define a plane that cuts through it. So 3 points give us a plane. They're coplanar. They also give us a big flat thing, and they'll all have the same common normal pointing up at 90 degrees. So if we think of our 3D object that we use to make up our ball in 3D, we could do that with a bunch of triangles. Now, if I could get you some really funky maths that would let you calculate off those triangles what the surface normals be, we'd really be in some luck. This funky maths that I'm referring to is in fact what's called the vector product. The vector product of two vectors gives us a third vector normal to the plane made by the first two. So I draw one, I draw a second, and now if I give you the cross product, as it's called, of those two vectors, I will give you a normal at 90 degrees to the plane that those two guys are on. And the magnitude of that will be absolutely affected by the angle between the two vectors. But I'll come back to that later in the class. This is pretty cool. But it is some pretty mega funky maths that it's going to do your head in a little to actually do the cross product. But having said that, if you do the cross product, you will get the normal. And you'll get the normal to the third. I mentioned Bill before and his dog. Remember? Okay, the key that Bill came up through with while he was walking his beloved dog was to do with vectors and to do with the vector cross product. And the breakthrough was that A cross product B doesn't equal B cross product A. So if A cross product B equaled a third vector C, then B cross product A actually equals minus C. That's right, minus C, going the other direction. Now this cracked the cross product for maths, and we found that you can suddenly get the cross product or the vector product to give us a normal. It gives you something at right angles to the first two, and if you get it around the wrong way, it gives you, instead of being the normal pointing up, it's the reverse pointing down into the surface. Okay, so let's look now at this super funky maths and the ways in which it gives you a normal.
Okay, I want to imagine that you have two vectors. I'm going to call the vectors R, and I'm going to call the vectors S. Okay, R and S. I'm going to try and find T. So, little diagram over here to think about this. This is one vector. This is another vector. And I want to find T. T is going to be coming up 90 degrees to that sucker and 90 degrees to that sucker. And I'm going to use for that the cross product. Now, the thing about the cross product is that we need to write out some vectors so we can kind of see what it does. So let's do that. Let's write out two vectors. I'm going to call them A, B, C, and D, E, and F. Okay, so two vectors. There are two vectors. I want this guy. So I need to do R cross product S. And what I expect to get out of that is T. Now, if I do that correctly with the right, if this is R and this is S, then that will be T. Because I did it run the other way, T would be going down, but I'll come to that. Okay, so R cross product T. How do I do that? Well, when I was doing dot product, I ended up with one number, but I know that I'm going to end up with a vector here. So the first thing I'm going to do is write down the framework of a vector, because I know the answer is going to be a giant vector. It's going to have three things in it. It's going to have an X thing and a Y thing and a Z thing. Now, I've been calling this the funky maths because, well, it's funky. So the way to think about this is that I could prove it, and I'm more than happy to do that as a tutorial or something, but it is actually just easier to take this one on blind faith straight out of the gate and say this is the magic formula, the funky formula that solves the problem. Okay, you want to multiply cross products. I always think cross, yeah? So we're going to start with B. I'm going to go, the first one is going to be B, and it's crossing, so it's going to cross with F minus C crossed with E. Okay, so that's going to be the first part of our vector. Now, and this is important, whatever we do, the middle bit's going to be negative. Okay, so it's going to be negative. We need another cross now. So the next cross we're going to do is AF, CD. So AF, and just as we did before, it's minus CD. Okay, now the third one is going to be positive, so it's always positive minus positive. And so the positive last one is going to be another cross. So we're looking, we've done the B cross, we've done the A cross. So we've got one more cross to go, and that's AE cross. So it's going to be AE minus BD. You can see why it's called the cross product, can't you? And so that's literally what happens. That is the formula. That's the way that it works. So I'm going to give you an example now. So let's just go to another one, another blank. Okay, so I'm going to do exactly the same thing with real numbers for a second. Okay, so there's R, and we're going to write out that vector, because it'd be quite useful to have a nice vector that we could work on. And then we're going to have S and write out that vector. And then we're going to get T out, and that T is going to be that thing we did here. And we know whatever we do, the middle bit's going to be negative. Okay, so like that's like before we do any math, we know that that is the case. Okay, so let's do a real worked example. Okay, so I'm going to do 0, 1, and I'm going to do the other vector as -1, 1, 0. Okay, so those are just two kind of vectors. I'll do another one in a second, but there's just two simple vectors to get us going, and I'm going to do them as a cross product. And so I'm going to come down here, and the first thing I'm going to do is 0 by 0, so 0, 0, and then I'm going to do -1, 1. Now the next one was -1 down to 0, and that was going to be -1, 1. Okay, done that one. Now that one, next one, the one that was left was -1, 1. So that'd be -1, 1 minus, a lot of minus ones going on here, isn't there? 0 minus 1. Okay, so we know anything multiplied by 0 goes away, right? So that's going to go away, that's going to go away, that's going to go away. So T is going to end up as -1. Okay, negative, negative, negative. So that's going to be -1 and -1. Okay, well, that's pretty interesting. So let's go and do another worked example, only with numbers that have less zeros and ones in them. So I'm going to try and draw one for you. So let's do a three-dimensional little graph here. Okay, so that's going to be X, that's going to be Y, and that's going to be Z. Okay, so I want to do some vectors. So I'm going to do R, and I'm going to do S again. Now, I'm going to pick my 3 points in 3 space. And I'm going to have R as -1, 1, and 0. And I'm going to have S as -1, 0, 2. Okay, so we can do this, right? Let's say this is like 1, 2. That's like 1, 2, 1, 2, 1, 2, 1, 2. Okay, so can we work out where -1, 1, 0 is? Sure. -1 goes back into negative on X. I'm going to go up 1. So it's kind of up here somewhere, and it's 0. So there's the point there. It would be like notionally along from here and notionally there. Okay, so what's the other vector going to be? -1 again. I'm not going anything up in Y, but I am going over in Z2. Okay, well, that's going to be over here somewhere, right? Because it's going to be like notionally across there and there. Okay, so now if I was to actually draw those 3 points, being 0 being the third one, let's do that. There it is there. There it is there, and there it is there. Okay, so we can sort of imagine that, right? It's sort of flat down here on that plane of X and Z, but it's leaning over a bit. So if I was going to do a vector, I'd sort of expect it to come up here, wouldn't I? Like a vector kind of up this way, if that's a flat plane, leaning back a bit. All right, let's see what the maths gives us. So I'm going to do the cross product to get the normal, and the cross product is going to be, start with this, 1, 2, 0, 0. Okay, well, 1, 2 minus 0, 0, which is 0. We don't care about that. We know the middle bit's always negative, so I'm put a negative straight away. I'm going to go -1, 2, which is -2. I'm going to minus, well, 0 by -1 doesn't matter. It's going to be 0. Okay, and then finally I'm going to go -1 to 0, which is nothing, and 1 minus 1, but it's minus minus 1. Okay, so what's that equal? It's going to equal 2. That was minus 2, but it was minus again, so that makes it 2. And that was minus 1, but it's minus again, which makes it 1. All right, well, let's see where that got us. Okay, so we're going to come over here 2. We're going to go up 2. And we're going to come forward 1. And voila, there it is. So that's the normal. Obviously, it would be at right angles there, and it would be right angles there. And that's a vector that's sort of coming up. If I draw it more sort of heroically, that's a vector coming towards camera a bit. Up like that. Okay, so the maths works, and it is funky. I totally give it to you. And I'm just going to go back and quickly show you that again here, just because this is the formula that we need to pay attention to. Let me just mark that out in a different color. So we're going to take the B, and we're going to do a cross product with the F. So that's this one, BF. And then we're going to do the other half of the cross, which is CE. They're minus. And they're all going to be minus, but the middle one is a negative to start with. So the second one is going to be a cross this way. There's that cross, AF, CD, minus again, but the whole thing is negative. And finally, we need one more cross, where we can do A by E. We haven't done that one yet. There you go. And we can do the corresponding B by D. Now, if you want to try and remember it, if you think of this as just a pattern, because some of you guys are like me and much better with pattern recognition than you are with anything else. A, B, C, D, E, F. You have to find crosses. Well, that's a cross. Yeah? Obviously, that's a cross. But the next cross is going to be that cross. Okay, that's the middle cross. And then the final cross is going to have to be the only other cross left on the board, as it were, which is AEBD. The reason for that is that if you tried crossing C with anything, well, you can't do a cross, right? You know, it can only go up. So if you've got downstrokes, the only downstrokes you have is BF, AE, and AF. So you know you're going to do that. So you just have to get the right order then. And so I always just go from the B to the A, and of course I know there are two A's, because the only way you can do crosses. So to simplify things in your head, when you're looking at this, just always think to yourself, well, there's the first cross, there's the second cross, and there's the third cross. And then you've got the cross product. Of course, in a lot of maths, you'll end up writing that as like hard coding. But as long as you do that, you'll get the funky results. Okay, if we go back to our vectors R and S, I'll do the cross product of those to get vector T. Well, the magnitude of T, if you like, the length of T, remember we looked at those before, that's actually related to the angle between them. So if we call that angle theta here, and this is T, and this is R and S, then as we vary that angle, as we get the angles closer together, in fact, T gets less magnitude. The direction remains the same, but the magnitude becomes less. And it's actually the case that we can work out that the magnitude of T is actually equal to the magnitude of R, dot product magnitude of S, and it's by the sine of that angle. So I'm going to call this angle now beta instead of theta because it makes things simple. And that's the angle between the two vectors. Now this is really important. The fact that I can get the magnitude of T by using a dot product lets me relate cross products to dot products. Now, of course, if I was using dot products, of course I'm going to get a single number out, right? So we sort of know that without looking at any maths, if I'm going to have a dot product of two vectors, I'm going to get a single number. We know that the sine of an angle is a single number. So I'm going to get a number out. I can't get a vector out, but that number is the length of T. So that's pretty important and incredibly useful.
Okay, you still with me? So we've got a set of points now. The set of points make up a little bunch of triangles, and then if we do our really super cool stuff, we get the normals to the triangles. Then we can then interpolate between them, and bingo, we have Gauss shading. And that's when they all start to fall like dominoes. This is it. This is like the point at which you become a pagan maths god in a 3D visual effects sense. But just one point before I go on, before you become pagan gods, we need to know the order in which to multiply A cross product B. Now, to do that, we use what's called the finger tool. Yeah, you write it. This is my hand, okay? Hold your hand like this, if you call this vector A and this vector B, then your thumb is the direction that vector C will go in. And if you kind of reverse them, then it would go the other way. So A cross product B is going to give me C, B cross product A is going to give me C. Now, of course, inside the computer we have slightly more complicated, funky stuff to manage that for us than holding our hand up. And in some textbooks you'll see this written up as the screwdriver rule. But hey, that is it. Once you get the dot product, which gives you a scalar number like we did last week, and the cross product, which gives you a vector, you can absolutely blow the lid off a whole bunch of stuff. So, Phong shading. It's one of the more simple types of shading that comes right after Garot. We looked at highlights last week, and we saw that highlights and reflections and stuff were able to be calculated using these techniques. So a specular reflection, like on this mirror ball, is a reflection of light. So I've got a light up here, and I actually bounce off that perfectly, and I can see the light reflected in the ball. It's the angle of incidence equaling the angle of reflection. We've already done that last week. Now, how do I go about getting myself something that's maybe a little less mirror-like? Now, I've been using this as a sort of diffuse ball, and it is, but of course there are some spec highlights on this, but they're kind of fuzzy. I can't see, like I can off the mirror ball, what's going on with the light, but I get a ping kind of highlight going off. And that dot is caused by the specular highlight, but unlike the mirror ball, it's a blurred spec highlight. Now, this can be explained by the existence on the surface of what's called microfacets. So we assume that each surface in the real world isn't perfect, and so we don't get perfect reflections. We normally get these microfaceted little things. So what we're going to want to do is work out the reflection, work out the normal, but then we're going to have to basically have a kind of a distributed profile, if you like, of what the spec highlight should look like, an approximation for this. The degree of which the microfaceting is kind of perturbing and screwing up the normals and stopping it from being a perfect thing. In other words, the roughness versus the smooth. I mean, like matte paints have a very high microfacet, and obviously gloss paints are much cleaner. So that spec highlight is going to be derived from an equation which is going to work off all the maths we've done to date. Phong shading is really just a reflection distribution function. And so the basic principle of it is exactly what we did last week. An estimate, if you like, of the surface normal to each vector in 3D, and then the averaging of the surface normals over the polygons at the point at which they meet. And then we have these estimates and we use some lighting calculations based on those to give us the Phong reflection that was invented 20 years ago. Okay, so the screen intensities are just going to be worked out by exactly the same maths that we've done to date. In fact, if you started looking into, and obviously this is not a 3D class, but if we started looking into all of this stuff, you'd find that nearly all of the hardcore lighting models are all using pretty much the maths we're talking about, the vector maths we're talking about, with dot product and cross product. So really we've solved the Phong shading problem, but if we went further and went right up to anisotropic sort of solutions, ones done by people like Greg Ward, really, really brilliant work, that all, if you just look at the maths, and I'm not asking you to sort of decipher it, but if you just look at the maths, it's basically dot products and cross products of the vectors. It's exactly what you'd expect it to be. It's like we've unlocked the keys now to both of the things we needed to do amazing work. Okay, so what are some examples, some practical uses of these? If I wanted to, say, model my iPhone, as we were doing last week, one of the things I'm going to want to do when I'm rendering it is, if you're the camera, you want to know whether this polygon is facing the camera and you should render it, and this polygon is facing away from the camera and shouldn't be rendered. This is a really simple problem, and very, very simple renderers tackled this a long time ago. It's the problem of just whether or not you can have a face that's exposed, the hidden face removal problem. And that can all be solved with, say, the dot product.
Okay, so now I want to do my iPhone. So I've got a face on my iPhone. Let's put a triangle over here. That's the little screen. And then the bit on the other side is another triangle, which I'm going to call the triangle to do with the edge. The camera's over here. And this is like if I was to draw my iPhone just miraculously in 3 space, it would be sitting there like this. And it'd have the Apple logo on this side. And on the other side of the iPhone would be this guy. This guy's normal is facing out here. This guy's normal is facing in here. Now, because we've modeled our iPhone out of simple triangles, all of the normals on that guy are pointing that way, and all the normals on that guy are pointing this way. Okay, but let's say, for argument's sake, just to be nice about this, I decide that I'm going to make my normals not be as obvious as 90 degrees to where the eye is looking. So just so I've got them sort of more randomly floating in space. Okay, so there's one here, and it's got its normals kind of pointing up like that. Yeah, and my eye is over here again, camera, whatever, looking this way. And I got another one that's just hanging out in 3 space back here, but its normals are pointing back that way. Okay, if the normals and the eye line is less than 90 degrees, it has to be facing the camera. And if it's more than 90 degrees, it has to be facing away. Think about it for a second. Once this vector hits here, if that angle is less than 90 degrees, it looks here like it might be about, I don't know, 80 degrees, then the thing has to be facing the camera. But if the normals are way more than that, so we've got a one coming in here, you've got all the way over here, that's 180 degrees practically, then obviously it's facing away from the camera. And so anyone you like to draw, once you know where the normal is, so they've got one here, and the normal is maybe coming up this way, in here is the vector, there's the other vector, that angle is probably, what, 30 degrees? It's going to be facing, this is facing the camera, that's facing the camera, and that guy, that's its back. And so it's really, really simple just to use dot product to work out whether or not the angle between any two vectors gives you a face that's facing towards the camera or facing away from it.
Okay, so we worked out some directional stuff, but there's a whole bunch more we can do. For example, that same equation that we looked at a moment ago that used sine, you're wondering where that was going to be useful? Well, we can use that for actually working out the area, the size of any triangle in our simple 3D geometry.
Okay, so let's do 2 vectors. And just to make life simple, I'm going to just, before I do anything else, I just want to review parallelograms. Don't ask me why just yet, but it'll become immediately apparent. Okay, just in case anyone forgot basic stuff, let's think about this for a second. There's a parallelogram, right? In other words, if these were made up of vectors, and I called that vector R and that vector S, then I just got another couple of them and stuck them on the other side. So that's also S, and that's also R, yeah? So clearly 2 vectors, imagine they actually connected here properly. 2 vectors, I just put another couple over the top. Okay, now, that's a parallelogram. If I push that up, imagine I was a little guy, came along here and pushed S so it was vertical. So let's try and draw this as accurately as we reasonably can. I'd have a square, right? Or rather a rectangle. S and R now. Okay, so the area of that's pretty simple, right? It's R times S. If they're vectors, well, that's going to be the magnitude of R and the magnitude of S, but that's okay. R times S. All right. When I push it over on its side, when it kind of leans over like this, I can no longer do R or S because clearly there's less space. I mean, eventually it's going to collapse and have no area in it at all. So it's leaning over. So what do? Well, as it would happen, if I was to take out a mathematical chainsaw and I was to cut off through here, lift this triangle out and carry it down and stick it on the end here, it would perfectly sit on here, right? This bit here would be this bit here, right? So that's fine, which means that I've now got a new rectangle. It's no longer this one, but it is in fact this distance here. Let's call that H by R. So now H and R, but of course, for that to be the case, what I really want is that to be the magnitude of R. That's fine because it's a vector, but that's fine. So literally if I got this height here and I used R, I'm going to get the, so if I do, and this has got nothing to do with vectors for a second, if I just got any parallelogram, right? Like that was 4 units and the height here was 3, then the area of that would be 12 units. Yeah? I mean, this is like the same as if we pushed it up straight and it, you know, was actually a square, was 4 and 4, it would now be 16 units. Okay, no magic there. So all I'm saying is that this height thing here is kind of significant. Now, and this is where you need to pay attention. Imagine that instead of drawing that chainsawed line through there, we just move it down. Obviously, that is the same distance, agreed? and that's h. And now you see why we get sine involved, because if that's beta, we know that we have got a relationship between angles that relates h over s, and we want to get h. That sine is going to give us h. Sine lets us unlock what the height is of a parallelogram. Okay, now without worrying too much about the details of all the maths involved, let's just jump right into what this is actually telling us. In fact, if we had a parallelogram like this, and that was beta, then we can actually work out the area of this parallelogram, and it's going to be equal to r by s sine beta. Magnitude of them. Why magnitude of them? Because they're vectors. Okay, so r's magnitude dot product s's magnitude times sine beta. So let's see why that might be. Okay, so let's just imagine for a second that I can say that r and s is just their magnitude, so I'm going to get too carried away here a second. What is sine of b? It's going to be h over s. Hang on a second, cancel those two out, I get RH. And a minute ago I just agreed that the size of this parallelogram was R by H, right? I mean, we draw a line down there and that's H. So that is the area. So that means that that is the area of this parallelogram. Brilliant. Sort of an odd way to write it, perhaps. It might seem a bit obtuse. Why, when I can write R times H, do I bother writing the magnitude of R by dot product the magnitude of S sine beta? Well, the reason is that that happens to be actually equal to the dot product of R and S. And that's really, really, really useful, because now we can relate the product of the dot product to the cross product. Okay, now there's one other really huge thing here. If I want to work out the area, I'll just change colors again. If I want to work out the area of this triangle, the one that's defined by the 3 points here. Remember I doubled it over here to get R and S? I remember I said I had another triangle the same, that just stuck out, another S, another R. Obviously that triangle's the same as this triangle. So in fact, the answer to the area of this triangle is half of that, or half of that. So now if you give me 3 points, either using dot product or using cross product, I can give you the area of a triangle.
Well, that's it for this week. I hope you've enjoyed Class 3. I've really enjoyed doing it. Please keep talking to me in the forums. I'm trying to modulate these classes in line with what you guys have been suggesting. Before I go, just one last favourite quote from that American guy about our old friend Bill. Remember I was telling you about Johann, the physicist that kind of popularised his work? He has one of my all-time favourite quotes from a physicist about a mathematician when he said, I think in referring to Bill, a mathematician can say anything they please, but only a physicist has to be at least partially sane. Until next time, I'm Mike Seymour. See you.